Swayam Prabha. Digital India. Educated India.
Good morning. This is the second lecture on computational fluid dynamics. The contents of the lecture are assessment of CFD in the analysis of turbomachinery, introduction. I'll discuss on governing equation in rotating frame of reference, algorithm suitable for turbomachinery applications. Then I'll discuss on boundary conditions applied to turbomachineries and the quality of means required. In the previous lecture, I have introduced introduction of computational fluid dynamics in brief. After this, the natural questions would be, why is CFD in the analysis of turbomachinery exceptional? Is it needed some special training or awareness while applying CFD in the field of turbomachinery? My response would be yes. The reason is, here the flow is very complex and the geometry. This is one of the most complicated flow that encounter in practice. Thereby, the algorithm should be suitable for turbomachinery application, and thus the boundary condition and the turbulence modeling, or if you perform alias in turbomachinery. In this lecture, I'll discuss some of these points, how to apply CFD successfully in prediction of turbomachinery flows. While discussing about the assessment of CFD in the analysis of turbomachinery, I like to say that the turbomachinery flows are among the most complex flows encountered in fluid dynamics practice. In most instances, they are three-dimensional, highly unsteady. The laminar, transitional, turbulent, and the separated flow are often encountered. The flow may be incompressible, compressible with subsonic, transonic, and supersonic regimes. In some instances, all the three flow regimes coexist in turbomachinery passages. Further, the flow suffers from effect of rotations, curvature, shock boundary layer interactions, and heat transfer. Here, the flow is highly vortical, such as secondary flows, tip leak vortices, trailing edge vortices, and the horseshoe vortices. Moreover, the flow may be single or multi-phase, such as liquid-solid interaction or the liquid-gas interaction, or there can be the phase changes. Furthermore, in a multi-stage environment, the flow is highly unsteady with stator-rotor interactions, while the free stream turbulence is usually very high. This stator-rotor interactions also is responsible for multimodal transitions where the flow is very complex. Thus, one needs to be familiar with the computational techniques adopted to resolve this fascinating flow field within the rotor passage or in a multi-stage environment. I like to state that CFD and turbulence modeling have reached a high level of maturity relating to turbomachinery. Nowadays, the Navier-Stokes solver are routinely applied while design and analysis of turbomachineries in industry. Furthermore, it is preferred to use the finite volume methods with time-dependent procedures. Here, the same code or algorithm is valid for low subsonic to hypersonic flow, steady or unsteady environment, external or variety of internal flow by changing the boundary conditions. Thus, I like to say, if one uses a time-dependent technique based on the finite volume formulation, he can easily tackle the different environments by changing the boundary conditions. Over last 4 decades, CFD applied to turbomachinery has made a significant progress in the following areas: algorithm development, grid generation technique to handle the complex geometry, development of zonal techniques, transition and turbulence modeling, multi-phase simulations, application of proper boundary conditions, pre and post-processing of data apart from computer architecture. So there is significant progress from algorithm to the computer architecture. In all of these fields, there are significant progresses and advancements that facilitate the sophisticated calculations of flow and heat transfer, both in subsonic, supersonic, and hypersonic regime within the turbomachinery procedures. A breakthrough has occurred in the development of large eddy simulation over the last 15 years, resolving the unsteady flows within turbomachinery passages at a realistic Reynolds number and free stream turbulence level. Furthermore, CFD plays a major role in the aerodynamic analysis and design of turbomachinery. The use of CFD by fluid machinery manufacturers has increased significantly over the past few decades. However, CFD results must be complemented with experimental observations to design and optimize blade configuration. Furthermore, the literature illustrates a significant use of commercial CFD software in the analysis of flows through turbomachinery. However, the major issues associated with the commercial CFD software used in turbomachinery are the computational time and accuracy. This must be addressed. Furthermore, in an unsteady flow, a solver needs to run for millions of iterations on a huge grid points, demanding the use of multiprocessor and multi-CPU in HPC application, which is not trivial with commercial softwares. Major commercial CFD softwares which are being used for turbomachinery applications are stated here. ANSYS CFX, ANSYS Flynn, OpenFOAM, these three softwares are being used. There are options for different turbulence model such as K epsilon, K omega, SST K omega, and RNG K epsilon models. This model can be easily adopted while conducting calculation using one of these CFD software. Furthermore, multiphysics, multi-phase simulation, research on combustions are feasible with these softwares. Now I like to say that the attention must be given regarding the governing equation in rotating frame of reference. We know there will be effects of centrifugal and Coriolis forces. Thus, we'll consider now the modification of Navier-Stokes equation because of introduction of Coriolis and centrifugal forces. Governing equation of fluid mechanics in rotating frame of reference will be explained now. The momentum equation in rotating frame of reference, neglecting the angular acceleration, can be expressed as rho within the bracket del W del T plus W dot del W plus omega cross R plus twice W cross omega equal to minus del P plus del dot tau ij plus rho g. This is the expression of momentum equation with rotation, equation number 20. Please note that del W del T is the local change of relative velocity. W bar is the relative velocity. W dot del W is the convective quantity. Omega cross rho is the centrifugal acceleration, the term 1, which is perpendicular and pointing outward to the axis of rotation, and twice omega cross W is the Coriolis forces, which is perpendicular to the plane described by two vectors omega and W. Thus the equation 20 represents the momentum equation in rotating frame of reference. As before, the right hand side of the equation represents the pressure gradient term, stresses, and the body force. Now I have indicated here a schematic illustrating the direction of Coriolis and centrifugal force. They are vectors. So I have illustrated the axis of rotation. This will be omega, capital omega. And with respect to the axis, I have illustrated the Coriolis and centrifugal force. W be the direction of relative velocity within the blade passage at a point. So P may be a point where I am considering. Now, omega cross W, which is the Coriolis forces, that will be perpendicular to both omega and W, that has been indicated here, while omega cross rho is the centrifugal forces. Here I have indicated centripetal forces that is directed towards the center along the radial direction. Therefore, centrifugal forces will act outward in the radial plane. So this is with respect to the direction of correlative and centrifugal forces that acts on a turbomachinery flows. Now I'll consider the different components of this momentum equation, and I'll put those equations in the vector form. We'll continue the discussion on Navier-Stokes equation in rotating frame of reference. The governing equations are employed either in the integral form while conducting the finite volume formulation, or in the differential form for finite difference formulation. Furthermore, the most appropriate coordinate system for turbomachinery is the rotating cylindrical coordinate system. Thus, the Reynolds average Navier-Stokes equation in a rotating cylindrical coordinate system can be expressed as del Q del T plus 1 by R del R of R into E plus 1 by R del theta of F plus del Z of G is equal to 1 by R into S. Equation number 21, where Q is the solution vector, E, F, G are the flux vector, and S being the source term. Now please note that I have indicated here the Reynolds average Navier-Stokes equation. Thus, I am writing down the equation for turbulent flow. Furthermore, it is a cylindrical coordinate system where R, theta, and Z are the axis, R being the radial direction, theta is the circumferential direction, and Z be the axial direction. And corresponding the relative velocity component can be given by WR, W theta, and WZ. Thus, please note that R, theta, Z be the axis here, and the corresponding component of relative velocity is equal to WR, W theta, and WZ. Thus, I can write here Q is a vector as rho WR, rho W theta, and rho WZ, and rho E0. E0 is the total energy. Similarly, E, flux vector, that is rho WR, and the second row would be rho WR square plus P minus tau R. Third row would be rho WR W theta minus tau R theta, and the next rho WR WZ minus tau RZ, and the energy component would be here rho WR0 minus WR tau RR minus W theta tau R theta minus WZ tau RZ plus QR. Similarly, I have defined F and G. Note that first row represent the continuity equation. These three would represent the momentum equation in r, theta and z direction, and the last one would indicate the energy equation. Now I'll have to define S0, which is the source term here, similar to the vector E and F. I have defined here G. Furthermore, the source term S has been defined, and please note that the component are 0, and in the R plane it is P plus rho W theta square plus rho omega square R square plus twice rho R omega into W theta, and in the theta plane it is minus rho WR W theta minus twice rho R omega into WR, followed by 0 and 0. Thus, please note that the source term contains the effect of centrifugal force and the Coriolis force. Now I'll indicate what are the centrifugal and Coriolis terms. Please note that the centrifugal component are centrifugal component rho omega square R squared will act in the radial plane. So I've indicated here the centrifugal force, and the Coriolis forces have two components. They will be in the radial plane and the circumferential plane. So I have marked the Coriolis forces by rad. So this is the Coriolis force in radial plane, and this is circumferential plane. Thus the Coriolis component will act along the radial plane and the circumferential plane. Therefore, I like to conclude here telling that centrifugal force will act in the radial direction, and Coriolis forces have two components, one in radial plane, another is circumferential plane. Furthermore, I have illustrated the stress tensor and heat flux vector tau theta theta, tau zz, and tau rr. There, the principal stress, while tau z theta and tau rz and tau r theta, they are shear stresses. And note that in this principal and shear stress, apart from the laminar component, there are additional terms which will appear because of turbulence fluctuation. Now let me explain about Reynolds decomposition. What Reynolds decomposition says that instantaneous quantity has been decomposed as proposed by Reynolds as average quantity. Here W instant INS means instantaneous relative velocity has been decomposed as an average part and the fluctuating part. The average part is denoted by capital W. This is the average part, and fluctuating part has been denoted by small w. This is the turbulent fluctuation. Now, this additional stresses, they are coming because of turbulent fluctuation. There will be rho W theta square average, rho WZ square average, and similarly rho WR square average. In the shear stress, the average turbulent fluxes would be, turbulent stresses would be rho WZ W theta, rho WR WZ, and rho WR W theta average. Thus, consider any component, say suppose WZ theta, there will be a laminar part and there will be a turbulent part. This is laminar component and this is turbulent stresses. Similarly, if you see heat flux vector, there is a laminar part and the turbulent heat flux. So rho W theta small e average, rho WZ small e average, rho WR e average. They are turbulent heat flux. Hence, what will happen because of this turbulent fluctuation? The laminar heat flux would be added because of this turbulent heat flux. L stands for laminar part and T stands for the turbulent component. Now in this expression of shear stresses and the heat flux component, we have now appreciated that because of turbulent fluctuation, there will be additional stresses and there will be additional heat flux quantities. This turbulent shear stress tensor and heat flux vector are evaluated by turbulence model. Thereby, a substantial model has been proposed to evaluate these turbulent quantities, that is shear stress quantities and heat flux quantities. Here I have indicated what are the independent variables appearing in the above equation, Reynolds average equation. They are WR, W theta, WZ, that means relative velocity component in R, theta and Z direction, apart from density, pressure, total energy E, enthalpy E0, and the turbulent shear stress, which are indicated by rho WI, WJ average, and heat flux tensor as rho WIE average. Now, as I have indicated, this turbulent stress and heat flux vector would be evaluated with the help of turbulence model. Now, an equation of state, that is P is equal to rho RT, Sutherland's law of viscosity, mu, and constant bundle number assumption will enable us to predict all variables for a laminar flow. For a turbulent flow, 9 additional variables such as rho Wi, Wj average, rho Wi, small e average have to be evaluated, which represents the turbulent stresses and turbulent heat flux tension. Many models have been proposed to mimic the effect of turbulence. Lately, large eddy simulations are successfully being used to resolve the turbulent stresses and heat flux tensions in turbomachinery flows. Based on the application, the following governing equation can be used. Suppose for an inviscid flow, we may restrict to an Euler equation, while for a viscous flow, we may adopt Navier-Stokes equation. Furthermore, the simulation could be two-dimensional or three-dimensional based on applications. To predict turbulent flow, we may use RANS for a steady situation, or to predict unsteady turbulent flow, we may adopt unsteady Reynolds average Navier-Stokes equation, which is referred as URANS. Furthermore, the governing equation may be in the fixed frame of reference while resolving the flow past a casket. Apart from the governing equation could be cast in rotating frame of reference while resolving the flow through a rotor. In a multi-stage application, continuous shifting from a fixed frame to the rotating frame is needed to resolve both the flow through the stator and the rotor. In turbomachinery, the flow conditions vary widely. Situation may demand the prediction of inviscid flow or the prediction of a highly turbulent viscous flow. It may be needed to solve subsonic to hypersonic regime. Furthermore, it may need multi-phase simulations. Often, we restrict to casket predictions. Situation may demand for multi-stage prediction illustrating complex blade-wake interaction. Thus, algorithm considered in case of turbomachinery analysis should be suitable to tackle all this variety of complex environment. So that's why we select algorithm, we design algorithm based on the need of turbomachinery analysis and turbomachinery flow environment. Both the pressure-based method and density-based method are used for turbomachinery application. Among the pressure-based method which are successfully used for turbomachinery analysis are listed here. They are simple algorithm, that is semi-implicit method for pressure-linked equation, which is derived by Patanker and Spalding in 1972. MAC, that is marker and cell algorithm, developed in 1965. Fractional step method by Kim and Moen in 19 1985. All these algorithms are used for solving three-dimensional, time-dependent, incompressible Navier-Stokes equation. The density-based method is usually put in time marching technique, considering that a time marching method is valid for subsonic to transonic flow rigging. And among this density method methods which are successfully used for turbomachinery are listed here, and they are Lax-Wendorf scheme in 1964, predictor-corrector McCormack scheme in 1969, and Jameson algorithm developed in 1981. Jameson algorithm is very attractive for turbomachinery application when used with local time stepping, residual smoothing, and multigrading. This allows the faster convergence. Here, the advective terms are discretized with central discretizations, along with introduction some artificial dissipation. This artificial dissipation corrects the dispersion error. Density-based methods suffer from dispersion error associated with oscillation in the solution while resolving discontinuity. To mitigate this problem, Rowe has developed a scheme which is referred as Rowe upwind scheme. The present day challenge is to develop an algorithm which can capture discontinuities without oscillation, and at the same time it would be robust and fast. I'd like to tell you now about alias solver. Lately, the compressible flow, which is filtered Navier-Stokes equation, are solved by large AD simulations. Often, the algorithm named as AUSM and its family, developed by Mary and Sagat in 2002, are used in resolving the flow within the turbomachinery passages. Here, the convective fluxes are often discretized with the third order accurate schemes. So this is so far with alias for compressible flow applied to turbomachinery environment. I'll discuss now about mains and boundary condition. They are very critical issues while predicting turbomachinery flows. The quality of mains, that is orthogonality and uniformity, to be maintained to get a reliable solution within turbomachinery passage. While explaining the boundary conditions for turbomachinery blade rolls, I like to state that specification and enforcement of proper boundary conditions are very vital to accurately capture the physics of flow through a turbomachinery passages. The essential flow variables here are W, P, rho, T, K, epsilon, P0, T0 and H0, where W refer for relative velocity, P for pressure, rho for density, T for temperature, K for kinetic energy, epsilon for dissipation, P0 for total pressure, T0 stands for total temperature, while H0 is the total enthalpy of fluids. Furthermore, the computational domain and grids are two important issues. Here I have illustrated the domain for the simulation of flow through a cascade. Here I have considered a cascade for simplicity. You know, cascade is a series of blades. Furthermore, I have given the definition of domain. Domain is a confined space where the simulation to be carried out. Here I have considered the domain which has been indicated by the form line. You know, the pitch means the distance between two consecutive blades. So here I have considered one pitch. Thus, instead of several blades mounted in an array, I have considered one pitch for the simulations. Thus, I'll have to put some boundary conditions so that it can mimic the effect of number of blades on the row. Furthermore, please note that Cx represents the projection of chord on the x-axis. This is the x-axis and this is y-axis. Y is along the pitch. Furthermore, I have indicated the inlet plane and the exit plane, which is the upstream and downstream of the blades. The inlet and exit plane should be considered in such a way that it does not influence the solutions. Thereby, one should consider the inlet and exit plane at least 1 to 1.5 times of chord away from the blade. Rest other boundary conditions I'll discuss in details. However, please note that at inlet, we know the magnitude of velocity, relative velocity, is entering the domain and what flow angle. I'd like to explain further about the computational domain. Strictly speaking, the inlet and the exit plane should be located far upstream and far downstream of blades, such that the influence of the blade row under consideration is negligible. The computational resources makes it prohibitive to employ the ideal condition. Hence, most investigators usually locate the inlet and exit planes at about 1 to 1.5 chord upstream and downstream. Regarding inflow and outflow boundary conditions, one of the most important issues in prediction of flows through turbomachinery is prescription of inflow and outflow boundary conditions. The prescription of boundary conditions at the inlet and exit boundaries depends on the flow regime, that is, whether the flow is subsonic or supersonic, and also the nature of the equations. The total pressure P0 total temperature T0 or enthalpy H0 and the flow angle are specified at the inlet. Axial component of the inlet velocity is computed as a part of the solution for the subsonic inlet. For a supersonic inlet, all variables are imposed at the boundary. Similarly, if the axial exit velocity is subsonic, the exit static pressure is imposed and all other variables are extrapolated from the interior. For a supersonic exit, all variables are extrapolated from the interior. If the equation is solved in the rotating coordinate system, the inlet relative stagnation pressure P0R, temperature T0R, and the blade speed are typically prescribed. The static pressure is usually imposed at the hub, and the radial equilibrium equation is solved to evaluate the distribution of pressure at the inlet and exit. Here the radial equilibrium equation is given by del P del R is equal to rho W theta square divided by R. The infinite blade throw condition is stated as the periodic boundary condition is enforced upstream and downstream of blade in a cascade to simulate the infinite blade row condition. Regarding surface condition, the no slip boundary condition, that is WR is equal to W theta is equal to WZ is equal to 0, are imposed on the surface for the solution of Navier-Stokes equation. Typically either del P del eta, where eta is the direction normal to the surface, is assumed to be 0, or del P del eta is evaluated at the surface by solving the normal momentum equation. Furthermore, please note that the pressure and velocities are related by energy equation if the flow is assumed as inviscid and adiabatic. Thus, the pressure can be specified at the boundary from the derived velocity field by solving the Navier-Stokes equation. Furthermore, for an inviscid flow without injection, the velocity vector would be parallel to the surface. That is, the condition del W by del eta should be equal to 0. This condition should be specified at the surface for an inviscid flow. For the surface temperature, either the world temperature or the normal temperature gradient del T del eta is specified. Suppose for an adiabatic wall condition, del T del eta is equal to 0. For the non-adiabatic wall condition, it is necessary to carry out a heat transfer analysis to derive the wall temperature. as an example the conjugate heat transfer analysis, where the conduction equation along with the convection would be solved to evaluate world temperature. For turbulent flow, the equation of turbulent kinetic energy K and dissipation parameter epsilon needs to be specified at the boundary. Thus I have written here as, if the two equations model, suppose the K epsilon model is employed for turbulence closure, the constant values of K and epsilons are imposed at the inflow boundary based on the specified free stream turbulence intensity and length scale as K infinity is equal to 1.5 Tu infinity square into V infinity square, where Tu infinity stands for free stream turbulence level at inlet and V infinity means the inlet approaching velocity. Similarly, epsilon infinity is equal to C mu to the power 3 by 4 K infinity to the power 3 by 2 divided by L infinity. L infinity stands for the length scale, which is assumed here as 1% of the pitch of the blade. Please note that C mu is the model constant. Thus, I have assessed the value of K infinity and epsilon infinity at inflow boundary following the free stream turbulence level and length scale. For the length scale, here I have assumed something, that is, for turbomachinery flows, I have assumed here that length scale and inlet is about 1% of pitch. At the exit, a gradient boundary condition is often prescribed, that is, del K del S del epsilon del S is equal to 0, where S be the streamwise direction. At the wall, a boundary condition as K is equal to 0 and del epsilon del eta is equal to 0 is often applied. However, truly speaking, the boundary conditions for K and epsilon at the wall depend on the turbulence model used. Figure 2 in the next slides illustrates a LPT blade, and I like to say that a age grid is employed within the blade passage, and please note that the mesh developed here is almost orthogonal to the surface. The age mesh within the blade passage is developed here by applying the power law to the control function appearing in the elliptic grid generation scheme. The scheme is developed by Hu and Lee in 1991. Please note that the orthogonality, aspect ratio, and uniformity are well maintained. Further, I'd like to add that often an age grid is employed within the blade passage for turbomachinery applications. Further, a highly skewed, non-orthogonal, and highly non-uniform grid evolve spurious solutions. Thus, skewed, non-orthogonal, and non-uniform grid must be avoided. To predict viscous layer means near the wall is often stretched following a power law or even an exponential function. However, power law is more preferred than the exponential function. With the low REK epsilon model or with an LES, the near wall mesh resolution should be defined as del y plus less than 1. That means near the wall grid will be refined well so that it can predict the gradient of velocity profile along with the profile of K and epsilon parameters. Figure 2 here illustrates an LPT blade and the mains around the blade where the grid lines are almost orthogonal to the surface. Please note the grid near the leading and trailing edge, which are the critical region, and the orthogonality is also maintained. And also note that they are refined near the wall to resolve the velocity gradients and the turbulence quantity. I have tried to explain here in brief how to apply CFD in analysis of flow through turbomachinery. Thank you for listening.